In this video I'm going to be talking about ionization energy. So our aims at the end of this video are to be able to define ionization energy. Ionization energy is another one of those terms that you need to be able to give a definition for in an exam. Explain the changes in ionization energy across period 3. Explain the change in ionization energy down a group. And use ionization energies to predict electron configurations. So what is ionization energy? Well, ionization energy is defined as the amount of energy needed to remove 1 mole of electrons from 1 mole of atoms in a gaseous state. Now there are always 3 marks for a definition of ionization energy question. The first mark is to say the amount of energy needed. The next one is to say to remove 1 mole of electrons. And it has to be 1 mole, so that's what the mark is for. And the last one is for saying it's from 1 mole of atoms in a gaseous state. So that's the third mark there, the gaseous state mark. Now you can also write a definition of ionization energy using just symbols. And in fact, if you were asked to define ionization energy in an exam, you could just use this symbolic form instead. So if you're using X to represent an atom, you could say the ionization energy is basically the amount of energy needed to perform this this reaction. So X, which is a gas, goes to make X plus, so the positive ion, which is also a gas, plus an electron. So that is the first ionization energy. If you wanted to, if someone asked you what the second ionization energy was, you could say that the second ionization energy, if I just move this up, the second ionization energy would be starting with this positive ion here. So the second ionization energy would be X plus gaseous goes to make X2 plus gaseous plus an electron. And so on. So the third ionization energy would be taking an electron away from a 2 plus ion instead of a 1 plus ion. So for your exam you need to be able to explain the change in ionization energy across period 3. So here's period 3, so that's what we're going to be focusing on. And the ionization energy generally increases. Now there are a couple of exceptions which we'll talk about a bit later, but there's a general increase across a period. And the reason for that is, basically, if you're trying to remove an electron from an atom, then the number of protons in the nucleus is going to affect that. The more strongly it's attracted to the nucleus, the more difficult it is going to be to remove that electron. So as you go across period 3, there is a higher nuclear charge, there are more protons in the nucleus, and you can see that from the proton number. There's 11 in sodium, 12 in magnesium, 13 in aluminium, and so on across to argon. The other thing that would affect ionization energy is how far away the electron is that you're trying to remove. Now, as you put electrons into the orbitals as you go across, the electron you add isn't actually getting any further away from the nucleus because it's always going to be in the same shell as you're going across the period. So the electron is no further away. So electrons same distance from the nucleus as you go across the period. And because there are no extra electrons inside that shell, then there is no extra shielding either. And those are the reasons for the general increase in ionization energy across the period. However, there are 2 exceptions to this rule. The first exception is aluminium. So as you go across the period, the ionization energy will first increase to magnesium, and then will slightly decrease to aluminium, and then we'll start increasing again. And the reason why it decreased to aluminium is because we're going from an s orbital to a p orbital, and a p orbital is slightly further away from the nucleus than the s orbital, and so that electron is slightly more simple or more easy to remove than the electron that's in the s orbital. Now, to answer questions on this, it's very important that you state certain facts to get all the marks. The first thing you do when you're comparing ionisation energies is state where the electrons are. So you'd say, in aluminium, electron is in 3p. In magnesium, electron is in 3s. And then you'd say why that makes a difference. You'd say 3p is further from nucleus than 3s. Therefore, less energy needed to remove the electron. So those are your 3 marks for that sort of question. Sometimes only 2 marks, sometimes you'll be asked what the exception is and then to explain, and generally, your 2 marks are for this, stating where the electron is, and then for saying why that matters. This, therefore, less energy needed to remove is a given because it's your exception. So these are the 2 most important points you have to make when you're explaining the exceptions. The other exception to this rule is sulfur, and it's for a slightly different reason this time. So, as we've said, as we go across the period, ionisation energy will increase to magnesium, drop slightly to aluminium, then increase again to silicon, increase again to phosphorus, then drop slightly to sulfur. Now, the reason here isn't because of a change in orbital. We haven't gone from a p to a different orbital. It's still in the p orbital as we go from phosphorus to sulfur. So basically, when we're explaining why sulfur is different, we're going to be comparing it to the one before it, which is phosphorus. So why is sulfur different? Well, if we look at where the electrons are for phosphorus, we're just going to focus on the p orbitals. So for phosphorus, there are 3 electrons in the p orbitals, like that. But for sulfur, there are 4 electrons in the p orbitals, like that. And you'll see that the extra electron is now paired with another electron. And that added repulsion that will be formed from those 2 electrons being paired will push that electron away slightly, and therefore make it slightly more easy to remove. So again, if you're asked a question on this, you would first state where the electrons are. So you'd say sulfur electron in 3p orbital. And you say it is now paired. So sulfur electron is in 3p orbital and it is now paired. And then you say why that matters. And you say the added repulsion makes electron easier to remove, and therefore less energy is needed to remove it. Now if we look at the changes in ionisation as you go down a group, we're going to apply the same principles as to what makes an electron more difficult or easier to remove from an atom. So down a group, the ionisation energy decreases. And that's because even though there are more protons in the nucleus, the electron is going to be further away from the nucleus. So for lithium, you've got 2 shells, the 1s and the 2s. And then for sodium, you've got an extra shell of electrons. For potassium, you've got an extra shell of electrons, and so on. So for each time you go down an element in a group, you're adding an extra shell of electrons. And so that means not only are the electrons getting further away from the nucleus, but you're also adding more shielding inside those electrons. So to answer a question on this, you'd say, even though nuclear charge is increasing, the electron is getting further away from the nucleus, and there is also extra shielding as well, or extra electron shielding if you like. So we've looked at explaining ionisation energy across a period and also looked at the exceptions. It's likely you'll get asked a question on those. But another question you might get asked is to predict what an element is based on its successive ionisation energies. So you may be given a table of numbers that represent the first ionisation energy, the second ionisation energy, the third ionisation energy, and so on of an element. And you've got to use those numbers to work out what the element is. And what you're going to be looking out for are the big jumps in ionisation energy. And what those big jumps will represent is where you've moved from one type of orbital to another, or from one shell to another. Because as you go from one type of orbital to another, you are getting closer to the nucleus, and if you're going from one shell to another, you're going much closer to the nucleus, and so those electrons become much more difficult to remove. So if we look at this periodic table, where the jumps are going to be are going from P to S, and from S to the next shell down. So if we're looking at lithium, for example, the first ionisation energy would be nowhere near as high as the second one, because the first ionisation energy can be removing this electron in the 2s orbital, but the next one is going to be removing an electron in a 1s orbital, which is much closer to the nucleus than the 2s orbital. You've gone down a shell. So now we can look at an example of an exam question based on what we've just learned. So this question asks you to use your understanding of electron arrangement to complete the table by suggesting a value for the third ionisation energy of magnesium. So we need to use our periodic table to do this. So there's magnesium. And what we've got to think about is which electron are we removing when it's the third ionisation energy. So for the first ionisation energy, we are removing the 3s2 electron. For the second ionisation energy, we're removing the 3s1 electron, and for the third ionisation energy, we're going to be removing this electron here, the 2p6 electron. So there you can see we've moved down a shell now, and so there's going to be a big jump in ionisation energy. So the ionisation energy is not just going to be between 1450 and 10,500, it's going to be much closer to 10,500 than 1,450. If you look at the difference between fourth and fifth, that gives us an idea of what the difference between third and fourth needs to be. It needs to be much closer to the fourth than the second, this third ionisation energy. And I would say it's going to be about 8,000. So there's going to be a big jump from second to third, but then not as big a jump from third to fourth and fourth to fifth, because now they're in the same, those electrons have been removed from the same shell. So this question is asking you in the other way round. You're trying to work out what the element is based on the numbers that are given to you. And you can see that the big jump is happening between the third and fourth ionisation energy. So that means that the fourth electron that's removed is going to be in the next shell down. Now it tells you this element is in period 3, so that means the fourth electron is going to be in the second shell. So that's your neon, if you like. So that means that this one must be aluminium, because if it's aluminium, then the first electron that's removed is this one here. The second electron that's removed is this one here. The third electron that's removed is this one here. And then the fourth electron, you jump down a shell, and therefore it's much more difficult to remove. So that one must be aluminium. If you need any more guidance on ionisation energy, then please email me or come and see me at any time.